Let's take a look at theorem 4.6.3, which is another example of a proof by contradiction. Here, the theorem says that the sum of any rational and irrational number is irrational. So in other terms, if I added things like 3/2 plus square root of 2, since the first one is rational and the second one is irrational, then my solution is going to be something that is irrational. Now, I don't know what the answer is going to be here. I mean, we have to do common denominators and so on, but we know that the solution is going to be irrational according to this theorem. And this is a true statement, actually. So how do we prove this statement? Let's take a look at that next. To prove the statement, we begin by writing the words proof by contradiction again. And I'm writing a comment to you here to remind you that in order to show that this theorem is true, I'm going to be doing a proof by contradiction. You know, I didn't have to mention that comment since I wrote the words by contradiction up on top. So please make sure that you write this in your proofs. So what I'm going to do in order to do a proof by contradiction is I'm going to say suppose not, which means that I'm supposing for the sake of contradiction that the sum of any rational and irrational number is not irrational. Now let me break this down a little bit and simplify the expression. Instead of saying the words not irrational, I could just say something simpler, and I could just say that it's irrational. The sum of any rational number and irrational number is rational. Now keep in mind, this is not true. So it should lead to a contradiction. Now, in order to show this contradiction is true, or that the contradiction happens, what we're going to do is we're going to suppose that R is the rational number and X is the irrational number in question. So since they're saying add rational and irrational, let's just give them some names basically. So R represents the rational, X represents the irrational number that will be added up later on. And keep in mind that their sum, according to the statement, is supposed to be rational. So the summation R plus X is technically supposed to be rational according to the assumption that we just made. Now, R is rational, and also the sum is rational. So we can use the definition of the word rational to find integers a, b, c, and d, where the denominators b and d are not zero, such that R is equal to a over b and R plus X is equal to c over d. Remember, this is technically the definition of rational, nothing new here. Just got to be careful that we don't pick the denominators to be zero, but everything else is integer. So now let's take a look at the R plus X, which is supposedly equal to C divided by D. But R itself is A over B, so we can take that and plug it into the expression. And we get A over B plus X equals to C over D. This is true by direct substitution, which means now I can subtract the AB fraction from the left to the right side of the equation. So keep in mind that X represents the irrational number, and all of a sudden now we have X equals to C over D minus A over B. What my goal is to write C over D minus A over B as a fraction with integer numerator, integer denominator, and the denominator is not equal to 0. If I can do this, then I would have proven that the X is a rational number, which contradicts the fact that I'm writing over here that it should be an irrational number. It's very simple to add the C over D minus A over B. All we have to do is use some algebra of fractions and turn it into BC minus AD, all divided by B times D. Now again, A, B, C, D were all integers, and on top of that, B and D were not equal to 0. So that means that the numerator of this fraction is an integer, and the denominator of this fraction is also an integer. Not only that, but the denominator is not equal to 0. Because B itself is not 0 and D itself is not 0, the product will not be 0 by the zero product property. So this leads me to believe that X then must be rational, because it's the ratio of two integers and the denominator is not 0. This is completely false because we had assumed that X is irrational. So that's our contradiction. We had assumed that X is rational, so how could it be now irrational? So it means that the conclusion is the following. The sum of any rational and irrational numbers is rational is false. it's leading to a contradiction. So that means that the statement of the theorem is actually